All right, welcome. Today we're going to put on our detective hats. Why? Because we're on a case to uncover the real story, the one that's often locked away, hidden deep inside raw data. So let's get our investigation started. It's a serious question. Think about it. If you're making huge decisions based on your data, you absolutely have to be sure you can trust it. But the truth is, raw data can be a really unreliable witness, full of misdirection and, well, half-truths.
I want you to picture raw data like a chaotic crime scene. You've got clues scattered everywhere, but a lot of them are misleading. Some are just flat out missing, and others are just random noise. Trying to make a critical business decision from that mess, it's like trying to solve a case with contaminated evidence. It's a total recipe for disaster.
So, what's the first job of any good data detective? You gotta secure the scene. Before we can even think about solving the case, we have to meticulously go through our evidence and clean up all the clues. So on the left, we've got our first suspect, incomplete data. These are those super frustrating gaps and missing values, the holes in the story that can send you down a completely wrong path. And on the right, you've got its partner in crime, data noise. This is all the random static and meaningless junk that acts like a thick fog, hiding the real clues we're trying so hard to find.
So how do we cut through that fog? Well, one of our key tools is called data smoothing. It helps us filter out all that random noise so we can actually see the pattern underneath. Think of it like this. You're averaging out the daily temperature changes just to see the bigger seasonal trend. We're looking for the big picture, not all the tiny random jitters.
All right, so we've cleaned up the most obvious messes. But now we're facing a whole different problem. Just too much information. Way too many variables. This is where a great detective knows how to separate the critical leads from all the background noise. And that process? It's called data reduction.
Okay, one of the most powerful tools in our kit is something called Principal Component Analysis, or PCA for short. Now I know, that's a mouthful, but the core idea is pretty simple. It helps us see the forest for the trees. It takes a huge data set where everything seems connected to everything else and kind of distills it down to just a few powerful independent factors. Those are the principal components that explain most of what's going on.
So here's what that actually looks like. On the left, you've got this complex web of interconnected data. On the right, that's the result after PCA. See? It finds the most important patterns and just boils them down. For a business, this means we can build faster models and make way clearer visuals, focusing only on what truly drives results.
Now, this isn't some kind of magic trick, it's a very systematic process. The method kicks off by putting all the evidence on the same scale, then it finds the center of it all. From there, a series of really clever mathematical steps figures out the main directions of the data and rebuilds it along these new, much more informative lines. The end result? A cleaner, simpler data set.
Theory is great and all, but let's actually see our detective in action with a quick little case study. We're going to crack the code on a small data set right now just to see exactly how this whole thing works.
So here's our evidence. We have 6 data points, and each one has 2 dimensions, or features. You can think of them as 6 clues, each with an X and a Y coordinate. Our job is to find the main direction that these clues are pointing in.
First things first, we find the average for each dimension. This gives us the mean vector, which is basically the center of gravity for all our clues. Finding this center point is the absolute first step to understanding the overall shape and direction of our data.
Okay, the next step is to completely shift our perspective. By subtracting that mean from every single data point, we recenter the entire cloud of clues around the origin point, 0. This kind of standardization makes it so much easier to analyze their true relationships without being biased by wherever they started.
Okay, so we've seen how to reduce complexity to get the big picture. Now let's switch gears to another core detective skill, interrogation. Sometimes the most powerful insights come from just questioning one variable at a time. This is what we call univariate analysis.
A classic interrogation tool is a simple frequency table. For example, say we have a list of IQ scores. Just by grouping them up and counting, we immediately see that the most common range is between 126 and 133. It's a simple first step, for sure, but it instantly gives us our first solid lead, the most common characteristic of our subjects.
During any interrogation, a detective is always on the lookout for what just doesn't fit. The weird stories, the alibis that don't quite check out. In the world of data, we call these the outliers. These are data points so far away from the rest that they just demand a closer look. So, how do we systematically spot these unusual suspects? Well, we use this really robust technique that isn't fooled by extremes. First, we line up all our data points, all our suspects, from smallest to largest. Then we just divide them into 4 equal groups, or quartiles. Now, this range between the first and third quartiles, called the interquartile range or IQR, is absolutely critical. It basically defines the normal territory where the middle 50% of our data lives. By focusing on this core group, we get a really stable measure of the spread that isn't easily skewed by a few weird suspects hanging out on the fringes.
So using that IQR, we can now set up some fences. We calculate a lower boundary and an upper boundary using these standard formulas. Any data point, any suspect that falls outside of these fences is officially flagged as an outlier, something worth investigating.
Okay, so far we've cleaned the evidence, we've reduced the noise, and we've interrogated single variables. But the real story, that often emerges when we start connecting the dots. This is the final act of our investigation, looking for the relationships between 2 or more variables.
Let's be super clear on the difference here. Univariate analysis on the left, that's like interviewing one witness to get their story. Bivariate and multivariate analysis on the right, that's like getting all the witnesses in a room together to see how their stories intersect and influence one another. It's where we discover cause, correlation, and all those complex interactions. And this brings our investigation full circle. Remember PCA? Turns out it's not just for data reduction. It's one of our best tools for multivariate analysis. It takes a confusing cloud of high-dimensional data, which is impossible for us to even visualize, and projects its most important features onto a simple 2D map that we can understand. At the end of the day, that's what this entire process is all about. It's a detective's methodology. It's how we make sure that the story our data is telling us is the true story. It's how we move from a chaotic mess of raw numbers to a single, trustworthy narrative that can drive real-world decisions. We've walked through the whole detective's guide, from cleaning the evidence and spotting the outliers, all the way to connecting the dots. The methods are right here. So the only question that's left is, what stories are waiting for you to uncover in your own data?